with that, I will start, I will start the event for you now. So before I start, just to let you know that this is a hybrid event. So obviously, there's quite a few of us in person. There's a few people online. For those of you joining online, thanks for joining us today. Please keep microphones on silent as usual. Okay, so with that, thank you everyone for being here. Welcome to this event sponsored by IMSI. We are the Institute for Molecular Sciences and Engineering, and this is the launch of a briefing paper. We're very happy to be here in collaboration with one very nice institute of the college, the Brahmal Vasudevan Institute for Sustainable Aviation. And so it's a pleasure to welcome you to the event today, where we're going to discuss low-carbon aviation fuels. And this is a briefing paper. You have sort of the summary on your desks, and there will be a nice panel discussion afterwards. I am Professor Amparo Galindo. I'm a professor of physical chemistry in chemical engineering. I am also one of the 2 co-directors of IMSI. So in IMSI, as I told you before, the Institute for Molecular Sciences and Engineering, our remit in the college is to draw from the strengths of our 4 faculties to address global challenges where an understanding and controlling of the molecules plays a central role in delivering better solutions. We work collaboratively across the college with an aim really to integrate people in a diverse way and to include everyone in the processes and works that we do. And so this is part of our mission, is collaboration, and so it's very nice that we could collaborate with this new institute today to present to you the briefing paper. So I think this is all I'm going to say. It will be Professor Rafael Palacios who will chair the session today. The theme of the briefing paper is very close to his research, so we're very lucky to have him. And with this, Rafa, I hand over to you.
I believe I don't need that one, right? Is it good? Thank you. Hello, everyone. Professor Rafael Palacios, Department of Aeronautics, and the director of this new Institute of Imperial. It's an exciting day for me because this is officially the very first time we have this logo anywhere. It's the first official event in which the institute, the new institute at Imperial, the Baby Institute, participates on a research activity. Let me tell you a bit about it. So it's new, it's cross-disciplinary, and it's trying to tackle the challenges to meet net zero in the aviation sector, as obviously the name says. Exists because of a philanthropic donation. So the gentleman that we named the institute after came to us with a substantial donation to actually make the institute and the activities happen over the next multiple years. So we have a 10 years horizon now and continuing after that. So that's going to be fantastic for us to draw it. Brahmal was here yesterday, actually. He's an alumnus of my department. Any of you finishing your degrees, don't forget us when you do well. It's very pleased to see them coming back after many years and actually revert back to us. The Institute physically sits, of course, within aeronautics. We open a space for it. We've been working how we could accommodate activity. We have a space for about 8 to 10 people, but currently it's me shaping it, putting adverts together, and trying to get that capability happening. The first question I got, and I got this a few times by now, is you already work in the Department of Aeronautics. Weren't you working in sustainability? The answer is, of course we were. But what we didn't have is the framework to do first activities which happen beyond the core remit of aerospace for many, many years, which was about efficiency, how you better aircraft. Sustainability was always an afterthought. If they are better, they should be more sustainable. So how we can feed that back. And the second is, of course, that we enable to have a reference center within the we enable us to have a reference center within the UK and European environment, which so far didn't exist at the academic level. So it gives us the opportunity to really lead these from the front and lead this from a research-based institution like ours. The final, and this is where I spend most of my time since we started officially last summer, is that allows us to really reach out beyond the confines of the aeronautics department. So by definition, institutes and Imperial across the fundamental and cross-disciplinary, like the Institute of Molecular Science. So that we have now a very nice platform to really reach out, engage with other academics, and build up from various expertise. Why this is important? Because net zero in aviation, as you will see today, is really, really tough. Okay, it's one of the toughest areas to decarbonize. So we need to bring a lot of expertise. Good news, a lot of that expertise existed at Imperial in various distributed environments, and we have now a home for most of those activities. So we're going to be working with academics that are across departments. We're trying to look for synergies between the activities that happen between them, and we will start a new capability within the Aero department, looking specifically in the interactions of aviation and the environment. That's all I can say for now. So I will have lots and lots of things to report in the future, but we are starting as we speak. So what I would like to do next is to hand over to the two authors for the briefing paper team, Paola, Saenz, Cavazos, and Nadine, Moustafa, and they will give us the presentation on the highlights of this briefing paper. You can come over. Thank you.
Thank you, everyone, and thank you for being here. Thank you for the people that are online joining us as well for this briefing paper number 9, launch about low-carbon aviation fuels. My name is Paola Saenz, and this is my friend and colleague, Nadine Moustafa, and we are two of the co-authors of this briefing paper. Now, we're going to tell you a little bit about how we did this briefing paper and some of the results, but obviously we're not going to give you anything because we want you to read it as well. So it's just a little taste of it. We actually had the opportunity to go to a very interesting event organized by Innovate UK a few weeks ago, and there were some very interesting talks from very important people in the SAF industry. So we heard from the chief advisor for the Department of Transport in the UK, and we also heard from the director of bioenergy technologies from the Department of Energy in the US. And it made me put things into perspective. So just to think about how important the results that we're going to present to you here today are. The reality is that people are going to continue flying. So even after a massive hit in the number of flights due to the COVID-19 pandemic, the flight forecast in Europe to 2050, even in the lowest case scenario, is going to continue to increase. So at least 20% compared to 2019 levels. And even though the recovery has been slower than expected after the pandemic, according to the most recent report of the International Air Transport Association, they say they will reach pre-COVID pandemic levels by 2024. So now what's the challenge? That, well, the aviation sector actually pollutes a lot, and it's actually very hard to decarbonize. So aviation contributes to 2.1% of the CO2 emissions globally, and it also represents 12% of the CO2 emissions of all transport sources. And it's also very hard to decarbonize because essentially, emissions from aviation are all over the place. Not only from the feedstock extraction to produce the fuel, to its refining, to its transport, to the airport hubs and distribution centers, but also in the combustion of the aircraft, where we have CO2 emissions, of course, but we also have the non-CO2 emissions, which actually represent 2/3 of the climate impact, whereas the CO2 emissions are only 1/3. And the problem with the non-CO2 emissions is that they're very hard to account for because they depend on many different things. They depend on the altitude at which the airplane is flying. They depend on the weather of that specific day and also where the plane is flying. So it's a very hard to account for. But there are some solutions being put up, and what are we doing about it? The UK recently in 2022 released their Jet Zero strategy to deliver net zero aviation by 2050. And they included a range of possible abatement measures. Now, those include market-based measures such as ETS and CORSIA, which is essentially improving these carbon-based measures, so enhancing the effectiveness of the emission trading schemes in the UK, and also working collaboratively with CORSIA, which is a global trading emissions scheme. They also want to use fuel efficiency improvements, as we heard from the beginning. That's also very important, and that's been in the works. And then, of course, we have the zero carbon aircraft, which is essentially an aircraft that uses hydrogen as a fuel. And then we have sustainable aviation fuels, which are the ones that we're going to be talking about today. And we have, of course, the abatement outside aviation sector. So the paper is actually entitled Low Carbon Fuels, because we consider the sustainable aviation fuels, which include biofuels and the power to liquids or synthetic fuels. But we also focused on hydrogen, which would be used in the zero carbon aircraft. And if you can see in that graph, it's around 21%, both the zero carbon aircraft and the SAFs, that are going to be so they're going to be representing 21% of that abatement measures by 2050. So there are some very important questions that we need to ask ourselves, whether we have enough feedstock and energy in order to meet this demand and in order to be able to get to those numbers. So those are one of the few questions that the briefing paper tries to answer. And I'm going to give you a little bit of an introduction of the three different fuels that we attack on this paper and that we talk about. So first of all, we have biofuels, which essentially they can be made out of any biomass-derived feedstock, but actually in the UK mandate, it requires to be from waste. That's another question that we answer in the free briefing paper, whether we have enough waste in the UK to actually meet this fuel demand. And in order to convert this biomass into a fuel, it needs to go through a conversion chemical process. Now, there are 8 pathways certified at the moment for biofuels that are compliant with ISO standards and that are considered drop-in jet fuel, which means that the aircraft doesn't need to undergo a redesign, but they actually can be blended with fossil fuel kerosene up to 50% and then be ready to use in the jet engine. Then after biofuels, we talk about power-to-liquids fuels, also considered synthetic fuels or e-fuels. And in order to do this, we need 3 main things. We need hydrogen coming from a green source. That's mainly using water and electricity to produce hydrogen via electrolysis. And we also need CO2 coming from direct air capture or other biogenic sources. And that undergoes also a chemical conversion. And the only approved pathway at the moment complying with ISO standards regarding power-to-liquid fuels is a Fischer-Tropsch synthesis. Now, that also gets, similar to biofuels, gets blended with fossil fuel kerosene up to 50%, and it's ready to go as a drop-in jet fuel. We also talk, as I said, about hydrogen being used in the net zero aircraft. Now, hydrogen is not considered a drop-in fuel because actually the aircraft will need to undergo a complete redesign to be able to accommodate hydrogen as a fuel. It has many different characteristics compared to fossil fuel kerosene, and so therefore there's a lot of questions around whether this is going to be possible and also a lot of safety questions as well. And there are different ways to produce hydrogen. Some of them are greener than others, and we present here you the different ones. So we have the green hydrogen, which again is the one you use for power-to-liquid fuels, which is hydrogen produced via electrolysis. And then we also have the most normal ways to produce hydrogen, which is via natural gas reforming. And then we also have the gasification with biomass and coal. And to these last 2 that I said, if you add carbon capture and storage on that, they actually become a blue hydrogen. So that means that they have a lower environmental impact. And of course, we included a small commentary on battery-fueled or battery operating aircrafts as well, and then also hydrogen fuel cell operating aircrafts. We do not go into depth on those in our briefing paper, but we definitely do a small commentary and have a view on that. In terms of the technology readiness levels of these different technologies, biofuels, as you can see, is the one that has most certified pathways, and it's the one that has the highest technology readiness level as of today, followed by power-to-liquid fuels, which are both of them, again, the drop-in jet fuels. And then we have hydrogen, which still needs to undergo a lot of research and safety measures in order for that to happen. Now that you know which types of fuels are we talking about and why, I'm going to tell you a little bit about the objectives of this paper. So we looked at 4 main different pillars. The first one was sustainability. So we looked at different literature papers that looked at the life cycle assessment of these fuels and compared them to the kerosene baseline. And we found out that there was a wide range of values out there, and we also address this issue in our briefing paper, and my friend Nadine will talk a little bit more about that as well. The second pillar was to understand whether these fuels were scalable and what will the UK need in order for that to happen. So we calculated the feedstock for each type of fuel that the UK will need in order to meet the demand of 2019. And on top of that, we also calculated the energy requirements to produce each fuel. Now, for this calculation, we used not only the conversion process energy, but also, for example, in the case of power to liquid, what is the energy required from direct air capture and what is the energy required from the electrolysis process. So we added all that up, and we ended up with the total energy requirements for each fuel. And we compared that to the current UK demand. Obviously, in order for these to be low carbon intensity, it all needs to come from renewable or lower carbon electricity. So we did those comparisons there. Then that also addresses the scale-up thing and the technology readiness level. And then finally, we make some policy recommendations based on all the fuels, so what the UK needs in order to meet the scale of these fuels, and also we made specific recommendations for each one of them. So now I'm going to pass over to Nadine, and she can tell you a little bit more about it.
Thank you. Thanks, Paola, for the extremely extensive and descriptive introduction. So the next part of the presentation includes essentially a brief overview of the results that we show in our report and paper. And I just wanted to quickly recap a figure that Paola already showed you, but essentially what I wanted to show here is that the first part of our report was assessing the environmental impact of the different low-carbon fuels that we've looked into. And one thing to note is that a lot of the, as Paola already mentioned, a lot of the environmental impact estimated by different literature out there or research out there varies considerably. And the main thing to kind of consider is that the assumptions can be different for all of those different research. And one of the main assumptions is essentially the system boundaries, but also the data and the data that you use and input into your model. And the 2 main system boundaries are well-to-tank and well-to-wake, where well-to-tank includes feedstock extraction, transport, fuel refining, and transport to the actual aircraft in the end. And well-to-wake includes all of the steps that I've just mentioned, but also the combustion of the fuel in the aircraft. And so we've come up with this figure that shows the environmental impact of all the different fuels. Essentially, we've plotted the environmental impact in terms of grams of CO2 equivalent per megajoule fuel. And we've looked at all the different technologies that have already been mentioned, so hydrogen, biofuels, and PTL, for different studies. And the number of studies are shown on the top here. Now, the red shaded box is essentially the environmental impact of kerosene, which is the conventional fossil fuel that we use at the moment. And that data is well to wake, so it includes the fuel combustion part. Now, all of the data that we've accumulated from literature is well to tank, and that's because studies either take it as zero for hydrogen's case, take the environmental impact of fuel combustion as zero for hydrogen's case, or assume it is zero for biofuels and PTLs due to carbon accounting models. So, for instance, they use market-based measures or DAC to assume that it's zero. Now, starting with hydrogen, which is shown here in blue, we've looked at different processes and fuel pathways for hydrogen. The first one being hydrogen from methane reforming without CCS. And with CCS, you could obviously see that the environmental impact with CCS would be lower due to the capturing of carbon dioxide. And then we looked into green hydrogen, which is essentially hydrogen from electrolysis. And we've looked into studies that use grid electricity, solar panels, and wind. Now, the most noteworthy thing is the one that's with grid electricity, where you could see that there's a large variation, but also it's noteworthy to see that the environmental impact for hydrogen from grid electricity is actually more than what you get for hydrogen from methane reforming without CCS, and that's largely attributed to the environmental impact of manufacturing of the electricity generation equipment. So, for instance, wind and solar. Whereas if you're only focusing on solar panels or wind, it's lower, and that's also depends on things like geographical dependence and location, and whether the country is already focusing on solar or wind, or whether they would have to actually build all of that from scratch. The next set of results are for biofuels, and we looked into different feedstocks as well as different processes. So the feedstocks we've looked into include algae, lignocellulose, oily crops, and forest residues. And the different processes include Fischer-Tropsch and alcohol-to-jet fuel. And again, the thing to notice here is that not all of them actually do that great compared to what we use currently as kerosene. Except biofuel from forest residues using the Fischer-Tropsch process. But it's also important to note that we need to really consider more environmental impact, so not just the CO2 emissions in this case, or the GHG emissions, but also things like the soil quality. So it would be really, really important, and this is something that we comment a lot in our report, to look into what other environmental impacts we need to consider and make sure that we're not burden shifting. The last part, is PTL for the Fischer-Tropsch process, power to liquid. And again, that does considerably well compared to kerosene. But I think one thing that I wanted to note here is the low number of studies. So this only had 2 studies that were published that we could find to our knowledge. And again, this would be extremely geographically dependent due to the need for low carbon electricity. Or renewable energy, and hence we would definitely need to invest and support more time and efforts into knowing the actual environmental impact for such processes before going into scaling it up massively. So the next part of our analysis included essentially looking at the resource demand and what we would need to scale those up meaningfully. Now, this analysis was essentially a hypothetical analysis to showcase what kind of numbers we would require. So essentially, we looked into what would be the resource demand specifically in terms of the current UK renewable energy production. For us to produce, for instance, hydrogen or biofuel or PTL, that would be enough for the 2019 SAF supply that we would need it in the UK. Again, this is hypothetical, and it's just to showcase the numbers. So this is in no way implying that the UK policy is that we would have to be self-sufficient in the sense that we wouldn't be importing any SAF from outside. But also, it's not to say that we would use one type of fossil fuel. Obviously, we would need a portfolio. But for this case, it was just to showcase what kind of numbers we would come up with. And we've looked into, again, hydrogen, PTL, and biofuels from different feedstock. So in terms of blue hydrogen and green hydrogen, to produce blue hydrogen, we would need around 40% of the current UK's renewable energy production just to produce the hydrogen that we would need to fuel all of our aircraft from the UK. And in green hydrogen, we would need 2.5%. Sorry, 2.5 times the UK current renewable energy production. And for blue hydrogen specifically, we would need 55% of all of the natural gas that we have in the UK to produce enough hydrogen to fuel all of our aircraft. So those numbers are obviously extravagant. And again, it is hypothetical, but it showcases the amount of work we would need to scale up such fuels. And in terms of PTL, the first thing that's noteworthy is that we would need CO2 from DAC and green hydrogen, which is currently not produced at scale in the UK, but also almost 5 times the current UK renewable production to fuel all of our planes from PTL. And in terms of biofuels, again, we've looked at the different feedstock. So, for instance, in terms of vegetable oil or oily crops, we would need half of all the agricultural land to grow enough biomass to supply our planes. And in terms of the other waste, the other waste feedstock, we would need anything between 8 times what we have in the UK, all the way to like 46 times the forest residues that we have in the UK to be able to scale up meaningfully those kind of fuel pathways. And when it comes to the renewable energy that we would need, it's anywhere between 1.8, for instance, that we've calculated for vegetable oil and oily crops, to 5 times the amount of current renewable energy production in the UK. So I hope this gives you a taster of the kind of numbers that we got and what we would need to scale up all of those fuel pathways in a very meaningful way in the UK. And so from our analysis, we've come up with overall policy recommendations that would work for all of the different technologies, but we've also come up with ones that are very specific to each fuel. And so the overall policy recommendations essentially include policy support for low carbon technology, but specifically looking into certain criteria. Where one, for instance, is already in the SAF mandate. So we want to make sure that it's at least 50%. It does 50% CO2 emission saving compared to kerosene. But also we would need to look into, for instance, other environmental impacts. So not just GHG emissions. And then that should hopefully include implementing more rigorous life cycle analyses, and hence, once those are done, we could support the development of infrastructure depending on the fuel pathways that we think are legit going to do this emission savings or environmental impact saving. And finally, collaboration with commercial entities is specifically promoting the information sharing between, for instance, academia and policymakers as well as industry. For biojet fuel specifically, so when it comes to standardized life cycle analysis methodologies, the main things we've realized is essentially looking into the benefits of co-products, but actually looking into them and making sure things like soil quality is not ignored, and land use change, which is considered in a lot of the life cycle analyses that we've seen, but not all of them. And finally, the time delay between CO2 photosynthesis absorption compared to actually how long it would take us to actually burn that fuel. And then improving biojet fuel production processes to optimize fuel to composition, but also to increase the yield conversion. And finally, look into ways to optimize the waste and heterogeneous sources that we would need for the feedstock. For PTLs, the most obvious one is to increase UK production of low-carbon electricity, but also scale up the production of green hydrogen and the scalability of direct air capture, since we need both hydrogen and CO2 for the scale-up of PTL. And also develop and essentially optimize novel fuel production pathways, because as Paola mentioned, there's only one certified fuel pathway route that produces PTL at the moment. And And finally, for hydrogen, again, we would need a meaningful scale-up in low-carbon electricity, but also green hydrogen and carbon capture, because again, we would need hydrogen and we would need to ensure that we scale up carbon capture and storage. And we could do that by optimizing things like adsorbents and absorbents. And finally, and most importantly for hydrogen, is promoting and supporting aircraft design, because again, as we've mentioned, that we would need to completely renovate the current aircraft design, because hydrogen is not one of our drop-in fuels. And yes, thank you so much for listening and coming in today. So please find our paper and find out more about what we've just said, but hopefully this gave you a nice taster of everything we've done.
Thank you to Paola and Nadine for this very nice talk. If I can invite the speakers to come over to the stage with me, please. You got it right? It's all right. It's all right. Better later than never. Everyone here. Let me introduce them in order from left to right. So we have Hannah Swindle, Head of Strategic Development and Air Sector Technologies at the BAE Systems. Professor David Simon Lee, Professor of Atmospheric Science at Manchester Metropolitan. Myself, you met me. Hannah Swindle, Head of Strategic Development. Sorry, I'm on the wrong one. Hazel Sofield. You're not in order here. Deputy Head of Low Carbon Fuels, Department of Transport, and Andrea Fantucci, Research Fellow, Department of Life Sciences. The plan is to have a bit of a discussion among us, part of the lecture. I have a few discussion points I would like to raise with the panelists. And then towards the end of the panel, I would also like to take a few questions from the audience. And please raise your hands. And a member of the team will bring your microphone. For those online, please use the comment section to pose your questions. And as we are limited on time, of course, we might not be able to go through all the questions as you would expect. So I can start maybe speaking on that side. What are the biggest barriers to bringing new fuels into vehicles? Hannah, you can tell us.
Yeah, so already from I guess I can speak from BAE Systems perspective, exactly. From a defence perspective. So there's obviously the qualification of the fuel. So already we know that 50% has been cleared, so that's great news. And obviously we're working towards that 100% qualification. So you've got the paperwork to cover first. And then there are obviously, so as BAE Systems, we're the integrators, so Rolls look after the engine, but we'll integrate the entire kind of airframe and everything together. And so it's understanding how that fuel behaves differently. So, you know, we do use the terminology drop-in fuel, but actually, you know, there are impacts. You know, I think the thing that's most common is around, for example, the seals and how they respond differently to the aromatics. So they're the types of challenges, but we're keen to face them. I think the realism is the supply chain, isn't it, for these fuels? But yeah, they're the kind of key things that I'd pull out initially.
If I can go to the other corner, so how we need to scale up, Andrea. So how we can go from the ideas that we have here all the way to getting BAE Systems to have fuel?
The point is that it's the limitation on the feedstock. So I think for each of the fuel, for each of the fuel that we discussed have different requirements and different restrictions. So in the case of hydrogen, you have obviously a requirement in terms of you're seeing the amount of electricity and resources necessary to produce the hydrogen, and those are very large, and several factors of the current available sustainable electricity. And so we need then to think about how you're going to scale up the electricity production to be able to produce the hydrogen that you need. And the other side is that hydrogen requires a large infrastructure change. And there's another factor that you have to take into account and say, you have to redesign the airplane. You have to think about where the tanks is going to go, because it has to be compressed hydrogen, it has to be liquid. If it's liquefied hydrogen, then it has to be kept at 20 Kelvin, and that means that you have to have normally a spherical tank that has to go into the fuselage that takes away passengers. And the other idea is that they put it on top of the head of the passengers, but that changes the aerodynamics of the airplane, increase the drags and so on. So there are several factors that you need to take into account for each of the fuel. In the case of power to liquid, you will have to take into account how much electricity you need, again, for producing the hydrogen, how much electricity you need to produce to capture the CO2. And those are quite large if we want to convert all of the fuel into sustainable aviation fuel. As for the biofuels, there are obviously several feedstock, but all of them, if you look at them, especially with the UK mandate that is excellent on saying that only waste material should be used, and in this case, we need to look at how much waste material there is. And we need first to think about what waste means. I mean, it's not waste in the way that people think that is what you throw away and then it goes into a landfill. Not all of these materials are real waste. So agricultural waste is what is left over after you take away your food, let's say. But this material is currently used. 50% is used for animal bedding food of the animals, and the other 50% is normally put back into the ground. If you decide to take it away, either you have to find a solution for alternative animal feeding, or you have to find a solution for not having the soil depletion. That means you have to increase fertilization. That means you're going to increase emissions as well. If you are talking about forest residues, again, obviously, we have to think about the environmental impact of that, of taking away, because, again, they are not waste. They are either left onto the ground to protect the soil, to recondition the soil, or used in other industries. But at the same time, we have to think about both of them, agricultural waste and forest waste, are extremely diluted in very large areas. So to collect them, it takes time, not just time, it takes also fuel. And you have to consider, especially if you're thinking, I don't know, about the Midwest, for example, where you're going to have in the US, a lot of agricultural land, but if you have to collect all of that and take it to one centralized point for conversion, then you have to consider all of the emissions associated with transporting all of this material. The other thing is that we also can look at what happens in applications where these biomaterials being used for energy production. Like in the case of drugs, they initially start using forest residues for energy production, but immediately they realized that it wasn't enough, and then they had to go to sustainable forestry because there is not enough material. It's very little and it's very diluted, and it becomes an issue of economy in terms of if it's valuable or not, and also if it's in quantity that it's sufficient. Then there is municipal waste, obviously, and then in this case it's where the quantity could be sufficient to achieve something, but it looks like, looking at numbers, that they are still on the short side, and you have to distinguish between biogenic waste from the non-biogenic waste. If you're using, first of all, it means that the people will have to divide it, and already in some council in London, you have the separation between biological waste and for the biological waste, you have to obviously think about where this biological waste is going. If it's going to landfill, then it's a good thing to divert it to something useful. But if it's going to compost production, then you will have to think about that you will have to use additional fertilization because obviously you take away compost from one side. So then in emission terms, you have to adjust and see what the real emissions are. The non-biological one obviously that carbon is embedded from fossil fuel, so it's not, if you release it, then it's not going to be neutral, it's going to be a positive emission. So each of them has challenges, and quantity is not just one challenge. As Nadine and Paola said, also heterogeneity is a challenge, especially if you want to do the conversion. So I would say, if science can help, is to try to improve efficiency of conversions, because those will reduce the amount of feedstock that you will need. And so in this case, and it will help in this case to try to get to a certain point.
Okay, thank you very much. A key element, Hazel, maybe you can give us your insight here, is of course the policy that goes around this, right? Where we are, what is needed, how these can be tackled at the UK versus international level. Can you give us a bit of the picture of where we stand on the policy elements here?
Well, as you say, there's a big job to be done here, and a lot of questions to answer as well, and those have been brought out very clearly through the information today. I mean, I think where we are at the moment is that we've said that there will be a UK SAF mandate, so that's about creating demand for SAF in the UK. We shortly will be publishing more detail on our plans for that. I think we've said a number of things about it, sort of set out an overall structure and a number of things, including the fact that it will be focused on waste-based materials, and we're not talking about getting rid of half of our food production in the UK in order to create SAF. So I think that's really important. So yeah, hopefully shortly we'll be publishing more detail on the SAF mandate, the kinds of trajectories. But I have to say, in developing that work, one of the big challenges we have is about how much feedstock will be available to us. And although there are some views and evidence that's coming through, such as papers like this, I think at the moment there isn't really agreement, and it is possible to find sources of evidence that say things quite differently. And that's one of the challenges that I think academia in particular can help us with is bringing that range down. There's never going to be one single answer, because we are in an environment where policies are changing. I note, for example, that we talk about landfill as the alternative for waste. Actually, the UK policy is to stop landfill, because landfill is such a bad thing. Although putting plastic in landfill seems like a good idea from a carbon capture point of view, it really isn't. So we're moving away from that. So actually, the alternative to disposing of municipal waste is actually energy from waste, so burning it and putting it up the chimney. That's very inefficient. So there are more complex arguments around that. I wouldn't like to say it was simple. As well as that, though, somebody's got to make all this SAF. They've got to make it at a cost or a price that is somewhat acceptable to those people who are going to be flying, because ultimately they will be paying for it one way or another. And therefore, establishing a UK industry in order that some of the value of all of that can be held within the UK in terms of jobs and growth in the economy, that's really important to us too. So we're looking at what we may need to do in order to help with that. Feedstock availability, I think I've already talked about, and really kind of getting things started. So we've also got our grant funding competitions, which are kicking off the industry, looking at the 100% SAF flight, which is going to bring an awful lot of interesting and very useful information around non-CO2 and other issues to do with high blends of SAF. So yeah, we've got a big job. There is a lot to do in a lot of different areas, and I think from our perspective, it's keeping all of those things moving forward in tandem that is the big challenge.
A quick follow-up. I mean, flying by definition implies going somewhere. So airplanes will go, they will load the fuel wherever you go, and then they will come back. How this is addressed on any policies in terms of production of SAF? Because they can avoid having to load fuel in the UK simply because half of the flights will happen by definition somewhere else.
Yeah. So I think, there's a big amount of work going on internationally, and actually personally not responsible for that. Other teams within the department deal with all of that, but we're absolutely aware that making sure that we're working kind of in tandem with what's going on around the world is really important, because if we do something that's very different, then tankering can be a consequence of that. And that is just inefficient, and therefore that's not a good thing. So I think we're very aware of that. I don't think we have all the answers at the moment, but it's absolutely being taken into account in what we're planning and doing.
Thank you. Absolutely.
So I think another thing to consider as well, linked to that, is, I guess, again, speaking from a defence perspective, within the UK, so for example, we won't always necessarily use RAF bases for refuelling. So there's an infrastructure, I guess, piece of work to be done as well around the timing, you know, and keeping in line with that and making sure that we don't cause ourselves problems by, you know, popping to an airport where actually we can't refuel anymore because we're not aligned in where we're up to in that phased kind of handover from a fuel to a different fuel. So there's quite a lot around infrastructure and I know it was touched on, but yeah, that's definitely another thing to consider.
Very, very important point indeed. David, we haven't talked so far here about non-CO2, which, as we saw from Paola and Nadine, is as important or more important than CO2. How we put that into the equation, how we define technologies that really don't have even a worse impact, because actually we may have a worse effect on the non-CO2 aspects of it. How the fuel can close the loop in technology development with the broader kind of impact.
Yes, thank you. I mean, just very quickly, thank you for the invitation here and the report. I think it was a really splendid report. There's so much consistency, I believe, between this report and the Royal Society report that Bill and I were involved with yesterday, launched. And the non-CO2 topic is very important in this. It's an incredibly complex area. Currently, it's 2/3 of the climate impact of global aviation. It is not a fixed number. If aviation went to a kind of constant level, the non-CO2 would equilibrate and the CO2 would become more important. That's because carbon dioxide accumulates in the atmosphere, so you get a switching of the importance. It's not a fixed fraction. However, when you have strong growth rates, because it equilibrates with the rate of fuel usage, the non-CO2 effect tends to gather steam and it goes faster. So at the moment, it's around 66%, according to our latest assessment, of the total climate effect if you consider effective radiative forcing. Now, how does a SAF affect this? Well, let's be very specific about what we're talking about. We're talking about bio-type fuels, we're talking about PTL-type fuels. So those two categories, which you nicely split off from hydrogen, are drop-in fuels. On the NOx side, as far as we believe, there will be no effect on the NOx. NOx is a beautiful subject. It's atmospheric chemistry, my specialism, and it's a very, very complicated topic. However, on the contrail side, which is my part-time occupation, we have huge, huge complications. On the face of it, if you have a drop-in fuel, you have lower levels of aromatic compounds, and we think it's the bicyclic naphthalines that are the primary cause of soot particles in the exhaust. Now, the soot particles, once they pop out with the water vapor that's inherently in the combustion, that condenses on the soot particles, they freeze, and then they grow into ice crystals. They become the ice crystal clouds that you see in the upper atmosphere. But sometimes they're there and sometimes they're not. Has it occurred to you to wonder why? It's to do with the atmosphere. It's strictly the ice supersaturation of the atmosphere. So sometimes they form, sometimes they don't. The line-shaped ones that you see that form quickly and then sublimate, they really don't matter. The ones that matter are the ones that last hours and spread, and you get this large coverage of contrail cirrus. We think those are the ones that are responsible for the vast majority of the warming signal from contrails. On top of that, they have different effects according not only to time, space, but in time. So there will be there'll be a complete warming at night, but that can switch to cooling at dawn and dusk, and it may or may not be warming during the day. It really depends on all the conditions. So all these conditions are highly complex. But if we have fewer soot particles in the exhaust, we have observed from in-flight measurements there are fewer ice crystals. So that's an observable fact. That's great. So that looks like it's going the right direction. We then get into the realms of modelling and we think that that reduces the forcing. However, I did say that this subject is complicated. If you drop the level of soot to a certain point, different microphysical mechanisms kick in with so-called chemi-ions and soluble type origin particles, and then they can increase the ice crystal concentration again. So if you drop the soot, it gets to an inflection point, and it can then go up again. All this stuff we just do not know enough about. And we talk about contrail cirrus as if it's a known quantity, and without being immodest, most people reference the international assessment that I had the privilege of leading. So they pick a number, and they forget the uncertainty bars. So, you know, this is huge. This is huge. If it's at the upper end, it's a big signal. If it's at the lower end, it's next to nothing. Yep. And then you have the complication. We change all the boundary conditions, and we're not really sure what is going to happen. We need those measurements. We need to be sure, because what I'm passionate about is that we don't make anything worse by trying to fix something. Certainly NOx and CO2, that is a big danger. Yep. SAF. Hydrogen, we're in the realms of we really, really do not know. We have no engines to test behind. We cannot measure things. We think that there will probably be larger and fewer ice crystals in hydrogen exhaust because the water vapor emission is about 3 times that of the kerosene burning. But then again, you know, we have to trust on all these models. Models are built on observations. They're not, you know, we try to avoid empiricism. But they are built on observations. We do not have observations, so we don't exactly know what will happen. So it's hugely complicated.
Quick follow-on. The 66%, where's the uncertainty bar on that one? Because it's a very nice number, but I guess it's...
That's an easy one. We did the relative uncertainty assessment on the CO2 number and the non-CO2 as a collective. Yeah. The uncertainties on the non-CO2 fraction of the total forcing are 8 times larger than that of CO2. We know what goes on with CO2. It's very tightly constrained. Non-CO2 is not tightly constrained. And then if you look at the probability distribution functions, I could say something like that to a technical audience like this. The non-CO2 is almost identical to the total PDF. It dominates the uncertainty signal. It's really, really large.
All right. I'm happy to take questions from the audience if any of you would like to raise your hand. Wasn't it? I think you need a microphone going for that.
First of all, I wanted to thank the presenters. I thought that was fantastic. My name is Washington Ochieng. I'm the head of the Department of Civil Engineering here. Let me say civil and environmental engineering, the E word. But I'm also the Senior Security Science Fellow for the Institute for Security Science and Technology at Imperial. So I've got an interest in resilience, defined as widely as possible. My question is about the value chain and the things that are being traded off here. And I picked up on the point that Professor Lee made about not making things work worse by thinking that we are fixing something. How would you represent the value chain, as in the different components of this problem? Not just the fuels. You got the engine, you got operations, you got infrastructure, and so on. And Andrea, you made the point about, you know, how you're going to produce hydrogen. Is that going to be clean? So what is the actual functional space, if you're thinking about this thing as consisting of variables that you're going to be trading off against each other, not just focusing, you know, on the fuels itself?
It's a hard question. Who wants to jump on this one?
I'll have a quick comment.
Please, yeah.
I'll have a quick comment on that. I have worked on non-CO2 atmospheric science for 30 years now on aviation, and I'm really, really keen on cross-disciplinary working. And essentially what you're asking is how we manage to do that cross-disciplinary working. And I'd say historically we've done it really badly. And what we need to do is do more of that. So, for example, do the people doing life cycle analysis of soils, do they understand where they fit in the rest of this discipline? Do my bunch, atmospheric chemists, understand where they sit? You know, do we know stuff about life cycle analysis of soils and land use change, which I would add is the most uncertain point about the boundaries of the LCA from a global carbon cycling point of view. It's getting these interdisciplinary connections, and we have to really work hard at our young generation of scientists to really get that point. And, you know, I'm sure you're doing fine work on doing that here. But to me, that's the most important point, is joining the dots, because we live in little silos with our specialisms.
I think from an industry perspective, it's the same issue. So, so BA Systems won't go into the detail of it, but we are trying to understand the kind of full life cycle analysis, for example, of our products and where we're up to with those. And I think, and speaking to some of the PhD students that worked on this earlier, there's not actually, a perfect model for doing that yet. And so I think there's a lot more work that needs to be done around the tools that we have available to do that, and the guidance that we have, and what we can follow as industry. And I know that obviously often comes from academia and joining the dots there first. But we're trying to do it at the same time. And it's very difficult to understand, like you said, that you know whether you're actually making a problem worse further down the line by making a change at one stage. So I think there's an awful lot of work to be done still.
I'm aware that Professor Lee has been at this game for a long time. And actually, my question was pointed because I believe the complexity or the hyper-complexity of this thing requires ownership. You know, somebody who leads from the front to be able to specify and then bring people together. And this is why the likes of, MMU and Imperial were invented, I think. This is what universities are for. But we have to work with the stakeholders in a way that works. So, I mean, what are the tangible steps that we need to make to make this happen, David?
Gosh, that's a hard question.
I can answer that one.
This is what
You
Brahmal
start an institute of
Institute-
sustainable aviation.
Promoting your institute.
That's precisely the point.
Yeah. I mean, these kind of activities and these kind of new initiatives and institutes are what we need. The only thing I would say in joining the dots is beware anybody that tells you they have a model that goes from start to finish, because they basically neglect processes in the middle. We have to continue to study processes at the process level, but we have to join these dots and understand each other. I mean, I'm working at the moment with a soil carbon specialist in New Zealand and a transport geographer on SAF. They don't understand what I'm talking about. I don't understand what they're talking about. But we're having to thrash it out, and we have to keep challenging ourselves that we don't understand what others, oh well, that's economics, I don't understand that, which I don't. I wish I did, but we have to keep doing this. Institutes like this, I guess, we're pushing the boundaries there, so that's great.
You from the government on this one?
Well, I mean, yeah, obviously it's the same problem in government as well. I mean, we have to work across everybody, with everybody, to progress the policy. All of the work that we're doing is absolutely sort of founded in the net zero policies, which sits in a different department to us, obviously. But it's also in our our wider aviation policy, which sits in a different team to us. I mean, this is about cross-government working from a policy point of view as well. And to the best of our ability, that is exactly what we do. Constantly, reviewing things with different teams, how these things fit together. Trying to resolve differences in approach and different priorities. How do you assess this priority against that priority? That's all very difficult and ultimately becomes political at that stage. But I think the government probably does have quite a machine that's already designed to try and do this. I think the extent to which it does that successfully all of the time, and I'll leave that to you guys to work out, but it's certainly attempting to do that and bringing people together, but certainly the complexity in here, if I think, even with the recent changes in government, you know, that added another different department to what we're trying to deal with. So it is complex and it is difficult, but we're certainly trying very hard.
So the division of the government departments is necessary, of course, because you need a structure. But when you go into these problems, how does it work, bottom up versus top down? Do you have a layer there that helps you?
It works both. I guess it works both ways and at all levels. That's the only way it can work. I mean, ultimately, yes, it's ministers who talk to each other at cabinet who make final decisions, but there is absolutely join up and working at all levels. There, within an individual program like ours, there are governance boards with representatives from all different departments. Yeah, there's a lot of different levels, and there's just individuals talking to each other and trying to understand the different languages that we all speak. So, yes.
If I may something.
Oh, please.
One thing, sorry, only about the value chain and the life cycle assessments. And one thing about life cycle assessment is that we should really look at life cycle assessment with a vision to scaling, because a lot of the assumption made in the boundary construction do not take into account the scalability of the process. Because let's say you're evaluating the land use change effects on one particular field, and you may have some advantages or disadvantages, but that might not be scalable or might not be representative, let's put it this way, to the other field where you're going to grow or harvest or do whatever you're going to do in other area or in other countries. So this vision of scalability is extremely important, because a lot of the variation you saw on the arrow bars in when you plot the CO2 emission calculations from LCAs from different fuels are not just uncertainty. It's not that the average of that is going to be the average of what's going to happen if you apply that to the whole world. But actually, there are very different scenarios representing very different situations where people have calculated according to specific conditions and specific fields or specific soil quality. And all of those factors are non-scalable, because there will be different soil quality in different places. And the same applies for certain assumption made in the life cycle assessment. That is what Nadine mentioned. That is the fact that the CO2 emission from the combustion of the fuel is at the moment not considered or considered to be zero, because the idea is that the CO2 in the fuel is what was before captured by the plants via photosynthesis. But the point is not considering, and because LCA normally don't do that, is not considering the time difference. And the fact that when you burn the fuel, you emit this CO2 in a very short amount of time, hours. But to grow the tree that is going to capture the same amount of CO2 is going to take years. So when we look at forests, then in this case we have to think that the time, there is a specific rate difference of reabsorption of the CO2 versus the emission. Now, it might be different for fast-growing things, but that needs to be addressed and measured and calculated, and it's not been done. So this differential of time is not considered. So at the moment, it's zero, and that gives you an advantage in terms of true CO2 emission, or sorry, the perceived CO2 emission of a certain fuel. And that's the crucial point, because all of this is to try to have net zero emission from the fuel. But if the calculation we do are wrong, and the assessment we do is wrong, and we don't have a fuel that is going to save us 80% of CO2, but is going to save us only 20%, then we are not achieving what we're trying to achieve.
Very good point. I mean, effectively, you go back to time zero and you have 1 million years, fossil fuel will go into net zero, right? So clearly we cannot put that into
Yes, exactly.
we have a question. You want the microphone, please?
Thanks very much. My question, I think, will build on actually this scalability point. My name's Kate Hewitt. I'm Policy Director at the Aviation Environment Federation. We're an NGO campaigning on aviation for people and the environment. I want to just say in relation to the graph that we saw right at the start of this presentation about demand, I think it's very important that we do not take those demand levels as a given. And I wouldn't be doing my job if I didn't say that before leaving the room. I think, Hazel, that you said at one point that we shouldn't be doing anything that will impose too much cost or impose a cost that's not bearable to people who fly. That's a comment that concerns me, because I think that in achieving net zero for aviation, we're going to have to do things that are probably expensive and certainly difficult. And that, yes, any kind of demand measure is difficult, so is all of this. That was just sort of by way of intro. But my question is about waste-based fuel in particular. I think, like Dr. Fantuzzi, I absolutely endorse the UK government's approach of saying we're not going to use crop-based biofuels and instead focus on, elsewhere in terms of SAF development. I think that's really positive. Nevertheless, I think that the evidence I had a quick look at this report this morning, and it was kind of endorsed by other recent research, the idea that focusing only on waste-based fuel is going to mean we're going to have very limited feedstock today and diminishing feedstock going forward. And I was interested in that context to see this policy recommendation that policy support should only be given in cases where the feedstock can be is scalable. I'm aware that the UK government has given, 165 million at the end of last year to the development of waste-based projects, fuel projects. I'm interested in the view of the panel, I suppose, on that decision and on whether there should be kind of future funding specifically for this waste to fuel concept, given that that's likely to be already a small and in future diminishing feedstock for SAF.
Do you want me to take that first? I can attempt to do that. I mean, I think the position we're in at the moment is looking at all the options. And obviously, waste is something where there are proven methods, processes of manufacture, even if that isn't scaled completely at the moment. And that is where the focus is. I think we also have policies that are helping us to look more closely at power to liquid fuels for the longer term, but I think we recognise the challenges that were presented earlier in terms of renewable electricity. We can't magically make all our fuel from renewable electricity today. That cannot happen. There isn't enough renewable electricity to do that, or hydrogen and carbon capture. All of those things are not there today, so that is not a solution right now. But the money that was allocated just before Christmas, it wasn't the whole 165 million, a portion of that, around half of that, to a number of waste-based plants, but also to power-to-liquid projects too, which will be longer term. I think we need a portfolio. We need to look at everything. I think there are different views about how this could be done. Current government view is set out through the Jet Zero strategy that it can be done in the way that was set out there, and therefore that's what we are working towards. But obviously, other measures could exist. I think I'd just like to come back on the cost comment as well. Certainly didn't want to sort of alarm anybody with that. I think recognising that cost is a big part of what we're dealing with here. Sustainable fuels do cost more than fossil fuels as we stand. Where those judgments fall in terms of what kind of cost should and shouldn't be put on to consumers will be part of the consultation that will be coming up. And of course, we'll very much welcome the broad range of views that we will get as part of that.
Can I just quickly comment on the cost thing? Because I think it's a very interesting point. one of the nice consistencies between Imperial's report and the Royal Society report yesterday is that there is no silver bullet, and we only have a range of technology options if we are serious about stopping digging fossil fuel out of the ground. It's very simple. Either we have a sustainable climate in the future, or we do not, and we have to pay for it. I would suggest that all these options are blindingly obvious that it will cost a hell of a lot more to fly in the future. Ergo, it will be priced appropriately. That will be the consequence.
Before we go to another question in the room, I'd like to take one of the questions from YouTube.
Please.
So this is an amalgamation of two questions from Jeffrey Maitland, who says, sustainable aviation fuels are all competing with the need for electricity, water and hydrogen in many other sectors. We can't consider these resource demands in a vacuum from other energy transition needs. How do we prioritise? So a nice easy one.
That's yours.
Okay.
No, I mean, obviously, this is what government need to do through their various sort of strategies and papers, and looking at the overall net zero, looking at how the whole economy decarbonises. You know, actually, if you ran a model and said, how do you decarbonise the economy, wouldn't you just go, well, let's not fly anywhere, let's stop that for a start. But that isn't going to be kind of a way to go that is realistic in terms of the world or the UK economy. So we have to sort of find ways about how we decarbonise as a whole, and which sectors decarbonise in sector, which ones go out of sector, and that is ultimately what we're all grappling with and will be for some time to come, I think. And we're all trying to do our own part of that, taking into account all the science, all of the evidence, all of the issues, all of the complexity, and plot a way forward with this. And obviously the range of different views that exist about how we should do that. So I think that is what we're grappling with, but of course there is no sort of magic answer right now.
The regulatory element is critical here, right? Say you force a particular, say, cost on rail because you want to make that green, and then people fly because you don't make that green. So you need to make sure that they are consistent across, right? That this is a key element of all this.
Yes, yeah, and across all parts, yeah, it's a many-faceted issue.
Okay. Well, this question here. Oh, sorry.
Hi. I think it's working. Thanks for everyone's comments. I guess it's kind of building on all the comments that have been made thus far. And this comments around sort of this whole net zero challenge, and it's a really cross-sectoral type of thing. And each of the issues we talked about already today about the scalability of the technology, you know, limited biomass, this is going to be across all the different sectors. And we're kind of right now, the discussion's focused on delivering net zero for aviation. However, we need CO2 removals, so you're going to need biomass for, delivering CO2 removals. You need to deliver energy in other sectors. Also, hydrogen needs to be scaled up for industrial decarbonisation, for transport decarbonisation. And the question is, you know, whether we are thinking in a joined up way, in a systems way, that when we're talking about scalability, you know, are we developing the direct air capture technology fast enough to deliver not just for aviation, but also for CO2 removals. And we often kind of design a mandate for, you know, for instance, sustainable aviation fuels, but have we thought about how that is synergized with the other aspects of scaling up, for instance, the GGR sector that would also be needed in order to give the amount of technology required for CO2 removals as well as sustainable aviation. Any comments around that? And I guess it's not just policy, but also from industry as well.
I'm happy. I mean, yes, absolutely, we've thought about all of that, or at least we're trying to. Again, no magic answers here about, you know, the perfect way forward. But you cannot develop one policy in a vacuum. It won't make any sense. It wouldn't be the right thing to do. So absolutely talking to colleagues on CCS, on direct air capture, on hydrogen production, on electrolysis, on power, on net zero, on, you know, absolutely all of the time, all of those things are integrated. I think one of the key things is the government has a planned and I think long delayed biomass strategy, which will help to set out the overall view of all of these things. And that is something, obviously, we're working behind the scenes with very much at the moment. So yes, we're attempting to do all of that. Will sometimes some things step forward quicker than other things, and there seem to be disconnects? Yes, there probably will, but absolutely we're trying to take all those things into account. I think the fact is we're all trying to do as much as we can right now to sort of address David's point that we've got to do something. Yeah, we're trying, I think.
Yes, please.
Also from the industry perspective, one thing that does help is the government catapults. So obviously they're not just aviation. So we're part of the high value manufacturing catapults and the connected places catapults, and the connected places are doing a lot around kind of sustainability, net zero initiatives. And so we're doing more to work with SMEs and kind of bring their ideas and technology in to look at where we can make improvements. So more than ever, I would say, especially for the defence sector, because we're naturally quite insular, we're doing more outreach and intentional kind of pan-sector working. And some of our relationships as well, I know from a BA Systems perspective, are intentional. You know, we've worked with Formula One teams around our kind of like systems for net zero and heat exchangers with reaction engines, completely different sectors. So we do a lot, and we're intentionally trying to do more. It's part of our strategy, looking at this.
I have time for a last question. Good. Get a microphone, please.
Hi there, my name's Alistair Lumsden and I'm from Carbon Neutral Fuels, and we're a power-to-liquid startup, and it's a really interesting field, power-to-liquids, because you're effectively converting one form of energy to stored chemical potential energy. And one thing that really drives that is the cost of electricity. And there's a big push from the UK government to sort of build up a domestic supply of sustainable aviation fuel. But the UK wholesale electricity market at the moment is a little bit bonkers, with prices going between £100 a megawatt hour all the way up to 200, or it's even peaked at over 500. It's quite hard for businesses such as myself to kind of go to investors and raise funds when the cost of our fuel is directly linked to the cost of electricity. Renewable energy is great, and the UK has huge penetration of renewable energy, especially with wind. But at this kind of latitude, it doesn't make sense to do solar. Solar is the easiest one for people to do privately. So if we, as a business, wanted to do some form of private electricity generation, solar would be the one to avoid this crazy price problem. Wind's very challenging to do. But one thing that seems like an amazing fit is small modular reactors. And there's a lot of startups now in that field pursuing Generation 4 small modular reactors. You're maybe talking sort of 5 to 10 years, but this problem's not going away in 5 to 10 years. I just wondered if anyone had any comments about the fit of, say, small modular reactors and power-to-liquid generation in particular.
We're exposed to this, but
Paola should answer.
I have a side work on wind energy, so I'm very familiar with that area. So small modular reactors are proposed as definitely one of the key elements for a sustainable renewable energy source. If you consider nuclear renewable, which I personally do, but that's up for discussion if you wish. Once you have that, it's a way to enhance capability, but the question becomes at the end the total needs. So this is all about, you need to supply 3 times as much electricity you have now with all those ingredients. At which scale you need to produce electricity, including modular reactors, wind, power, everything you can throw to this, such that you can supply to the electricity in the population and have the power to liquid. I think you have to talk through long horizons. There is very little to say beyond what happens in the very short term, I'm afraid.
Yeah, so I think complementing on that, exactly, you need to look at the total amount of electricity you need to produce the PTL. So, for example, you could use a modular reactor to power certain part of the value chain of producing a PTL. So, for example, you can have it powering, and again, maybe Nadine can help me with this, but when technology is at scale and you can use it to power, for example, your whole DAC plant or your whole electrolysis plant, then that would be useful, but essentially you need to think about the electricity you need for each part and make sure that that reactor is going to give you, so not only the conversion process energy, but probably the one for DAC and the one for hydrogen. Because as we saw, the feedstock on that in the UK and globally is just not there yet. So we're looking at the producers of PTL also having their own supply of direct air capture, of CO2 coming from direct air capture, and also green hydrogen.
And just to follow up on that in terms of the small modular reactor part, because I'm actually working on a paper with Energy Futures Lab on nuclear power. Small modular reactors, I guess, I mean, nuclear power in general is definitely something that we've done for a very long time. In terms of small modular reactors, it's quite novel. 5 to 10 years sounds ambitious, I think. But in general, the UK, for instance, wants to have 25% of its current electricity production coming from nuclear power. But having said that, a lot of the current nuclear power plants are going to be decommissioned within the next 10 years. So I think it shares similar problems to everything we've just been saying, and kind of comes back to that there's no silver bullet technology. And this is extremely geographical dependent, especially in the sense of nuclear power. So Asia, for instance, are doing amazing when it comes to nuclear power, and I think UK is looking forward to that. So again, geographically dependence and no silver bullet technology.
Just a very quick comment on that. Despite the fact I used to work in the mists of time for the Atomic Energy Authority, I can't comment on the nuclear side and small reactors. However, I'd like to draw a strand together from what you were talking about, PTL, to a strand that the lady over there, the yellow coat, was talking about. And we're talking as if our expectations are going to be the same in the future, and I think we have to recognise that our expectations cannot be the same, because you have to think about this from a systems point of view. And this point you were raising, which I thought was very interesting, about the kind of net zero concept. As an aside, go and listen to Miles Allen on the Grantham lectures about net zero. There is a difference between net zero and geological net zero, and we're talking about net zero when we all blithely talk about net zero. We're not talking about geological net zero. There is a big difference. But the development of PTL is interesting. I mean, thermodynamically, it's a kind of bizarre concept to slam carbon back into hydrogen and then blow it apart again. But that's what you're doing. You're reversing combustion. You're reversing combustion. So, but there's an expectation, but we need the DAC part of this, because go and look at the negative integrals on the 1.5 degree scenarios. The negative integrals post-2050 that most of the scenarios say that we need. So we will need DAC for other purposes as well. We will need that renewable hydrogen for other purposes as well. Most of the scenarios on the 1.5 with those negative integrals in the future for CO2 removal are relying on unrealistic amounts of BECCS. So it's like, you know, go think about it. There's lots of dots to be joined, so I don't have an answer to your question, but I think it draws out some interesting points about we need to, as the gentleman opposite was saying, you know, we have to think about value chains and joining the dots on stuff like this. And it is very complex, and we have to think about it.
With this, I think it's time to close this. So thank you very much for everyone to participate in the event, to the panelists, presenting authors for their comments. Thank you to the authors of the briefing paper, Andrea Fantuzzi, Michael Hai, May Bui, Isabella Will Rutherford, and Paola Saenz Cavazos, and Nadine Moustafa. Thank you to the Imperial AV team for making this happen, and to the people online to join us, and of course to the Institute of Molecular Science and Engineering for preparing the paper. Finally, thank you to everyone for attending the meeting in person or online, and please join us for refreshments and network outside. Thank you.